Okay, so thank you very much, everyone. And the title is, you know, finding what you're looking for. And so, what I'll try to do in this talk is to first try to just give a quick try to give an overview of what gravitational waves are and how we find them. And then I'll end the conversation with a little bit more kind of questions about where I see some of the limitations could be when we go forward. So, it's part physics and then part, more on the philosophy side. So do bear with me, but I promise no formulae, well, one very long formula, but we will get to that in a second. Okay, so
excuse me, is it possible to share the slides in the chat box?
I can send out a link
yes.
to them.
Yeah.
All right.
Yeah, it should be. It should be. Sorry about that.
Thanks.
Okay, so let's start with black holes and gravitational waves. So black holes, I'm gonna use a lot of videos to highlight my point. So basically, Einstein and the way he looked at space-time is really like a fabric. And so here you can see something, and when there's an Earth or something massive, it bends this space-time. And if other objects, they would feel this force, but it really is just a curvature of space-time. And so there's no real attraction in that sense. But there is a possibility, if you put enough mass into a single point, that you would be pretty much puncturing this space-time fabric. And that's really what is shown there. And let me just pause it here. So what a black hole really is a piece of space-time that is being cut out from the rest, just because the mass that was there in the fabric of space-time was so heavy, so concentrated, that it made a puncture in the fabric. So how do we know even that black holes exist? And I think this is still one of the most fascinating piece of relatively simple science you can do. And let me try to walk you through it. So before I start the video, here what you see in the colored dots are stars. Okay, so these are objects that have a little bit of light that we can see here from Earth, and this is actually the center of our Milky Way. Now you can see a big actual star-shaped, so not a star, but a star-shaped dot in the middle in the white. And what this is actually the central point that we think the stars are orbiting around. Now let me start the video. So here over time, you can see all the stars moving around, and we can track their motion as a function of time. And then that's what we're plotting here. And if we look at all the physics that we know, then we conclude that there must be something, that there must be something very heavy right at the point where there is the star-shaped symbol there. But we don't observe any light coming from that point. So we see light coming from everywhere, and this is an object that is heavy enough to heavily influence the orbit of all of these stars around it. And so, people kind of link the one concept of the theoretical concept of a black hole to this point that is here that seems to be very massive, but is somehow not emitting light. And ultimately, with also other discoveries of black holes, the Nobel Committee decided to give the people who made these measurements the Nobel Prize in 2020 for physics, and in particular for the discovery of the supermassive compact object at the center of a galaxy. Note that they don't explicitly use the word black hole here. And then Sir Roger Penrose for the discovery that black hole formation is a robust prediction of general relativity. So black holes are there. We have, other than this, also more evidence for that. And they are very interesting. Now, a few years, 2 years ago, this picture was all over the news. And what we're looking at here is almost an image of a black hole, or a reconstruction of how the black hole looks like, using our telescopes. And the real thing to see here is the little bit of a dark spot in the middle, which is the shadow of the black hole. And to make that a little bit more apparent, what we're looking at, let me start a video animation. So you've got light coming from all directions around the black hole, and this is typically from a lot of gas that goes around the black hole. And because of the curvature of space-time, also light is being bent. And so what we see is that light coming from different directions are bent in a way, but if we take the whole stream of light that is pointing towards us, we can actually, or we expect to observe, that there's a light ring, and then in the center there's a big dark spot, right? And that's how we would know that this was a black hole. And that's exactly what we observed. And so I would say this is the most kind of pressing evidence that we have for the existence of black holes at this point. This would actually be an image, if you were able to go close enough to a black hole, then this is what from simulations we would expect that you would see. And for those who've seen the movie Interstellar, this is actually, this was first calculated for that movie, and that we now have a little bit more understanding of. Okay, now there are more direct ways in which we can observe black holes. Rather than looking at its shadow, we can actually look at its effect on space-time. And if you accept the notion that space-time is a fabric, then there's a lot of interesting things you can do. And one thing you can do is really shake this fabric of space-time. And in the way that we're showing here, it's two black holes. They're orbiting each other, just like the Earth orbits the Sun. And this kind of vibrates the fabric of space-time enough so that it really sends out these ripples. And this is what we call gravitational waves. And now, in this case, because of the emission, the object gets closer and closer and closer until it collides and forms a single black hole. Now, these gravitational waves are a direct manifestation of space-time and are therefore closer linked to the actual physics that we are interested in, namely, the existence of a black hole. Okay, now again, if you were able to get close enough to the black holes, this is actually how it would look like, on the background of stars. So you would see the two objects, and you would see all these deformations around it, which is also a little bit what you saw with the light from the image of a black hole. But this is now with two black holes. And again, the orbit gets closer and closer to each other until at some point the two objects touch, collide, and then form a single black hole. Okay, now let's move on. So we've looked at the existence of black holes and also about the notion of gravitational waves, right? So black holes colliding to shake space-time in a particular way. And so we want to know, can we observe the effects of these gravitational waves? Because these are not ordinary waves, right? These are not electromagnetic waves that we can observe with telescopes. And so in order to understand how we can detect them, we have to first look at what is the effect of a gravitational wave. So here what I'm showing is a set of rings that, if there's no disturbance of space-time, this would be a cylindrical shape. So this would be a whole cylinder, perfectly circular in one dimension, and then a long tube in the other dimension. But as a gravitational wave comes by, this tube gets stretched and squeezed in different places, right? So it's really an elongation of space and a contraction of space in a periodic fashion. And that's what a gravitational wave is. And if you take this a little bit farther and you look at this would be the Earth, and you would send a gravitational wave along, then what you actually end up seeing is that the Earth itself starts to, I wouldn't say shake, but the whole shape of the Earth starts changing. Now, this disturbance of space-time is something that we can detect, and so we've built a very large detector in both the US and in Europe. And I'm just going to pause it here. So, okay, this is a good. So here in the center, I hope you can see my mouse. In the center is where the detector basically starts, and all the way here at the end of this video, you can see a little white dot here. That is one of the end stations, and the distance between the center to the end station is 4 kilometers. So we built a really large scientific experiment to measure gravitational waves. Okay. Now, the way it works is as follows, and in particular, we make use of the fact that you can shine light together, and depending on the phase of the light, you can actually end up canceling light itself. So you can make light plus light equals darkness. And we use this concept to detect gravitational waves. So let me try to explain what we're doing here. So here we have a laser that sends a laser beam, and what happens with this is, oh, this is a cut version. Okay, this is not very useful. Okay, let me try to explain it from here. Okay, so what we see here is a laser. The white thing is a laser, and it sends a laser beam to a so-called beam splitter. It splits the beam in two. One goes straight, one goes at a 90-degree angle. It hits a mirror, gets back, and then recombines here at the center. And the concept of measuring, these disturbances in space-time is if the distance between the mirrors and the beam splitter gets altered, then you see alternating, you see dark spots, bright spots here at this mirror. So we would normally keep it at a dark spot, so light plus light equals dark. But if there's any disturbance of the distance with the mirrors, then we see light, and we just record how this light flickers to detect gravitational waves. It's a little bit in the physics side. If you've done any physics, this is an interferometer. But if not, then the important takeaway message is that we can observe when the mirrors are moving through lasers. Okay, now let's take a look at the first detection of gravitational waves. And I apologize if there is also sound associated with it, so I hope it doesn't blast through your speakers. But let me see if, yes, there is sound. Okay, so yes, hopefully it doesn't come too loud, but let me try this. Okay, was that audible for people? No, okay, so there's no sound coming through the video. Okay, there was a sound through the video, but the important takeaway here is actually the waves themselves. And so here we see two detectors in the US, and you can see the wave here in both blue and orange of the wave that we saw. And one thing that made us quite sure that this was a detection is these detectors are 2,000 miles apart, and they saw the exact same wave coming through. And this is the first discovery of a gravitational wave. And again, we had associated this signal, this gravitational wave signal, to the collision of black holes. And this is actually an important aspect that I'll expand on a little bit more. But just by looking at the wave, we can infer that it was this process that I'm again just showing here because it's very pretty. I'm showing here as a collision of two black holes. Now, how do we know that? That's going to be a key question. Well, the way we observe gravitational waves is actually using a technique called match filtering. And what match filtering does is we take a stretch of data and we run the data through with something that we know. So what we know to be a gravitational wave, so the so-called waveform, and we run it through the data. And at certain points, there will be a higher match between what we know, our template, and the actual data. So let me show you exactly how this process works. So in blue, we can see the data, and in red, we can see, let's say, an example template, right? This is what we expect to see. And here below, you can see the so-called cross correlation. So how similar are the template with the data? And we slide the template over the data, and at some point you'll see a big spike in the cross correlation, and here it is, and then it dies out again. And it's these peaks where the data looks very similar to our so-called template, our expected gravitational wave signal. It's these peaks that we then take out, and then we further analyze them statistically to see what is the likelihood that this is a gravitational wave. So that's the process. And the way we know how gravitational waves work is either through a set of theoretical calculations, but mainly also through a set of simulations. This is an example where we simulate two black holes. And you can kind of see in color, and the arrows are different manifestations of space and time. And we just let these big supercomputers crunch through the numbers, say, okay, what happens if I put two black holes close enough? How will they orbit each other? And in particular, how will they distort space-time? And the simulation is going to run through a little bit longer, but at some point you're going to see the extreme curvature of space-time when you can see kind of the height coming up here. And this is when the objects gets really, really close. And you can see the whole space-time curvature, you know, in this case represented by the height. You can see them going up. This is the most extreme. You can see the arrows getting very extreme as well. And then it forms a single object. And then when we zoom out, and this happens in a second, when we zoom out, you can see the actual gravitational waves that are being calculated. And then here in the bottom, we can see the full waveform as a function of time. So that's how we extract the waveform that we then use to compare the data with. Okay, now indeed, as I was mentioning, in 2015, this was all in the news, and for the discovery of a pair of black holes. And this was big news. And in 2017, so a year and a half after the discovery of gravitational waves, the Nobel Prize in Physics were given to these three gentlemen. Okay, now the latest that we have now are about 100 confirmed collisions of black holes and or neutron stars. These are other forms of objects, and here's just an excerpt of their masses. So you can kind of see the higher they are, the bigger their mass. And so you can see 2 points going into a third point. And so these are the collision of the two black holes and then forming a single bigger black hole. Okay, now let's take a look going forward. And this is now where we get to the point where we need to think. So on the left and on the right, I'm showing future planned missions or detectors. On the left is the so-called Einstein telescope, and on the right is so-called the LISA detector. On the left, the Einstein telescope is envisaged to be 100 meters underground and fully cryogenic and you know, state of the art. On the right are 3 satellites that are sending laser beams over millions of kilometers, whereas we send laser beams on the left here on Earth over only the span of kilometers, right? And so these 2 different experiments are going to usher in a whole new era of gravitational wave detection. Right? The sensitivity for these detectors are at least 10-fold more than what we have seen before. And with this new sensitivity, we're also expecting to see things that we haven't seen before in gravitational waves. So an example here that I'm showing is a supernova. Right? This is a stellar explosion that actually can cause the creation of a black hole, or a neutron star. And these are the most, some of the most violent events that we know. But these events are very complex. So here is an attempt to simulate a supernova, and you can kind of see the very complex way in which the mass actually pulsates and oscillates in the star, and different ways of kind of keeping the pressure in until the full explosion goes. And all of this is done through large supercomputers to do the simulation. So you can now see the onset of the stars getting disrupted, and in this case a beamed explosion occurring. But you can kind of see that all the details of the mass in different colors. You can see that fine detail that we need to know before we can even make a simulation like this. Another thing that we expect to see is the collision of, or see more collisions of two neutron stars. So black holes are very simple in that sense because they don't really contain any matter. But if you have two stars, neutron stars colliding, then what we expect to see is actually a big explosion. Okay, and other than gravitational waves, there's also a lot of light, neutrinos, and other forms that are being associated with this explosion that we can also observe. But again, the introduction of matter here will make the whole system much more complex. Okay, now how do we do the calculations for these simulations? Here I'm just flashing a whole set of coupled nonlinear equations. Don't worry about it. I just wanted for completeness to show to people, these set of equations are the ones that we need to solve in order to simulate, these complex systems. And for those who are interested, this is actually coupling between general relativity, hydrodynamics, and resistivity, and really trying to resolve this on both the kilometer scale as well as the meter scale. We need to be able to resolve all the relevant physics so that we can account for things like vorticity and so on. Anyway, I'm just flashing these equations and many more. So these are very complex calculations. Okay, now let's go into the question of what I believe are some of the possible problematic things. So I think traditionally physics has always used simulations to, in a way to make predictions about what experiments we'll see. And we can link those simulations, and we can look at the data independently and say, okay, well, is there any evidence for this? But we are more and more moving into the era, as I've shown here, that we needed match filtering to get the data out, right? To even do the detections. And so we're now getting to a point where, in a way, the simulations determine what we can see in experiments. So no longer is it only used to do a verification, but more and more it is that simulations determine what we can see. And obviously this then leads us into a bit of a conundrum, because in the era of what I call a noise-dominated measurement, so it's very difficult to do these measurements, we need to compare with the source of truth to even be able to make that discovery, to make that detection. So the source of truth indeed dictates the discovery. But in our case, the source of truth comes from these simulations. And simulations themselves contain many simplifications. The problem is, when you need those simplifications, are you getting into a point where the simplifications become the truth? Okay, so it's a little bit of a vicious circle where we can only see what we put in. But if what we put in is based on simplifications and assumptions, and those are the only things that we are able to find, then are we converging ourselves into a point where we have made only discoveries that would fit these simplifications, not where these things break down, the situations where these things break down, and therefore the simplifications simply become our truth. And so, yes, the problem is when you can only guess reality through simulations, and these are, these are not necessarily an accurate representation of nature. And another thing that I think exacerbates this this problem is the use of machine learning. So computational cost of these simulations are very, very high. Okay, so some of the simulations that I've shown would take months, if not years, to do on the most powerful machines that we have, to do a single simulation. And so in order to simulate enough of these signals to be able to properly interpret the data, this would take us more than the age of the universe. So in a way, we only have a sparse representation of reality. Okay? Even if we were able to do a single simulation, we can't do enough simulations to really understand everything into fine detail, right? And this is withstanding even any assumptions that we've put into the simulations. And so machine learning is often used to bridge this gap as well. And machine learning is used to then, in this sparse information setting, to make predictions about, what does nature look like in between the simulations that we have done. And again, if we are in a system where we have sparse information and we use machine learning, we also end up maybe doubly reinforcing whatever we've put into the system is the only thing that we can get out. And so this is, I would say, machine learning is also an accelerator to this process where, we are more and more heavily reliant on just a few possibly, inaccurate representations of nature. So that's really where, at this point, I want to kind of, break this open and by the design of the organizers, really have a discussion about exactly this, right? So when we enter in the era of noise-dominated measurements, one can only find what one is expecting. But then we're also entering simultaneously in the era of limited predictability. Okay, whether this is at the limits of what we understand theoretically or at the limits that we can, simulate on a computer, we don't have full confidence in what we are calculating is really an accurate representation of nature. And so these two things, these two eras, when combined, I think could lead to a vicious circle where a real breakthrough science grinds to a halt. Okay, and then and for the machine learning part, I think this only amplifies this vicious circle. So I'd be curious what other people think about this. So I'll leave the floor to the organizers now.
Okay, thanks very much for that, Tjonnie. Shall we? Maybe we can present our little bit first, and then have a break before discussion. Does that seem good, Andre?
Yeah.
Okay.
I think so.
So I will share our slides. So really, we're just going to also say how this looks from a philosophical perspective, some of it at least, and hopefully talk a little bit more about how some new things might be found, but what exactly the kind of new things that can't be found by this process maybe. So let me see if I can screen share successfully. Too many windows open on my computer always. Okay, this looks good. Hopefully you can all see this, yes?
Yes.
Marvelous. Okay. So, confirmation. So a lot of people think that confirmation, or at least a very simplistic view of confirmation, is that it happens via making novel predictions. And it does seem that there are novel predictions being made in this kind of case that can be found. That they're predictions about wave shapes when particular kinds of events happen, say two black holes collide, or a neutron star and a black hole collide. What would the waves look like? What kind of shape would they have? You look for them, you can find them. So you can find what you're looking for, and that could confirm a theory. In a way, actually, I think you could say that the discovery of gravitational waves, some of the wave shapes, they confirm the existence of black holes. Now, I don't think that there's really much of a difference here with respect to the confirmation-related issues and a pen and paper model. So I don't think introducing simulations makes things any different. It's just that in this case, because the simulation is so complex, that it can be hard to work out what the problems are if you don't get what you're looking for. You know, if you've got like a simple pendulum or something model, it's very easy to see why if you've got a real pendulum, it might not work for it, right? I mean, you know, if there are things like air friction, if it's moving in more than 2 dimensions and so on and so forth, you can see how to alter the model. But you can't get that back and forth in this case because, as Tjonnie said, these sims take so long to run, very hard to kind of probe them. And I think it's worth adding as well that, look, some of the findings you can get via this process, they might be unexpected relative to contemporary astrophysics. So there's this one particular, I think there are a couple of events like this, but there's one in particular here, one event where a detected wave was attributed to a merger involving an object with a mass of around 2.5 to 2.7 solar masses. This is the GW190814, isn't it? Every event has a number. And this is very interesting because it's normally thought that neutron stars can't have such high masses. So there's a kind of theoretical limit. People discuss what is the theoretical limit of the mass a neutron star can have. Lots of scientific papers and that. There's some disagreement, but it's unusual to think that, you know, it can have such a high mass. On the other hand, though, no one's ever seen, I mean, at least by electromagnetic waves, no one's ever seen anything that looks like a stellar black hole, which has less than 5 solar masses. So there's some kind of discussion being prompted by this finding. So the question is, you know, is it the case that there are black holes much smaller than we've seen before, or is it the case rather that there can be neutron stars that have higher masses than we expected? It's a very interesting puzzle. So here's a case where you could, I think, find something unexpected or something that potentially challenges existing astrophysical theory. And also, of course, if you happen not to find any waves of the shapes that you predicted, then maybe that could lead to revisions in astrophysics too. And maybe in this case, you'd first expect there was something wrong with your simulations. But if you became convinced that your simulations were reasonably good, you might think, well, you know, I expect waves to have a particular shape, but we're not finding any waves of that shape. Maybe we're just finding waves of other shapes. That could lead to some revisions. But of course, if you don't find the unexpected findings of the kind that I've talked about here, where you just discover that something you already thought existed has slightly different properties, you know, different masses, or you didn't find things of particular shapes, that's not going to be able to do anything like disconfirm general relativity. And I think what Tjonnie is really pointing to as a big problem is that, you know, what about gravitational waves with shapes that we don't expect? There doesn't seem to be any prospect of finding these, because you've got to, you showed with that great graphic, you've got to take the template, as he called it, and go along and, you know, through and see if there's something that happens to, you know, match the template or potentially match the template. And you look in greater detail. We can't look for kind of unusual wave shapes, right? I mean, you can't just, you know, pick a random shape and then try to work backwards. I mean, ideally, it would be nice if we can find, oh, look, we've just spotted a gravitational wave with a shape we don't expect. And then you could try to kind of reverse engineer what kind of thing in nature, given our contemporary theories, might generate a wave with that shape. We can't do that. That seems to be a problem. Quite different from a lot of other previous science. So I think there's some reason to be pessimistic. You might say the kind of revisions we can expect to be prompted by gravitational wave astrophysics, at least at the moment, they're of a relatively minor kind. Maybe we're not going to find new kinds of things that way. We could just find that some things already in science's ontology have different properties than we expected, maybe. And perhaps you could make some calculations on frequency of events. I don't know about this, Tjonnie, you can tell us, but I suppose in astrophysics, some people might have an idea of how frequent they'd expect particular events to be. maybe you might find the frequencies differed, assuming your detection was a particular a particular kind of quality or rate. That might be harder to do, I guess. So maybe some optimism, though. I think as we push further astrophysics, I suppose it's going to be more a matter of using multiple investigative methods. And this is why people are talking about multi-messenger astronomy. And indeed, Tjonnie was talking about being able to look for things like supernovae and collisions of neutron stars, where you can use other kinds of viewing modalities and you try to piece it all together. And maybe it's not reasonable to expect it to be very easy for us to revise our theories. Right? We've saved so many phenomena. It's such a complicated system. I mean, failed predictions are not going to tell us exactly what went wrong. And that's kind of old news. When a prediction goes wrong, it could be that it can be you made some kind of mistake in analyzing the data. It could be the case that the model you've got to animate the laws is wrong, or so many things that could go wrong. But now we've got such a mess, if you like, such a complicated system, slower progress should be expected, I suppose. And then we go back to this question that are there new ways to use machine learning? I mean, Tjonnie suggested the way it's been used at the moment just compounds a problem, but we wondered if there are new ways that machine learning could be integrated or employed that might help. This is mainly Andre's area, so maybe Andre will have more to say about that. Okay, so that's kind of what we thought about it. I guess one of the difficulties we sometimes have, or will have, trying to communicate as philosophers and scientists is different languages, right? So we might discuss confirmation and truth in different ways, and that might create a bit of a stumbling block sometimes, but hopefully we can overcome that. Okay, so let's have a break now for